Assalamu alaikum. In this video I will be talking about boundary conditions and why it is important for ATOMSK and LAMMPS. So here you see that firstly we will talk about box vectors. So every box vector has an arbitrary component and an angle in contrast to LAMMPS. So what it means that in ATOMSK we can use any arbitrary component and angle for creating our box, but in LAMMPS there are some restrictions. The restrictions are that the first vector needs to be along the x-axis and the second vector needs to be along the xy plane. So to run this structure in LAMMPS we may need to rotate our system. So firstly we will be talking about the alignment of structure for LAMMPS. So here I have shown an example of creating a structure. This is a general structure. After that I will be rotating the structure. If you look at the code, ATOMSK -- create FCC, it means the type of the structure, 4.046 is the lattice parameter, aluminum, then we find rotate 45 degree y, rotate 45 degree x. It means that we will first be rotating the structure along the y-axis by 45 degree and then rotate the structure along the x-axis by 45 degree, and we will be saving our output file in aluminum.xsf. So here is the output file. So if we try to convert this .xsf file into LAMMPS format, we will see that there is an error. So how to bypass this error? To bypass this error we need to use the option align x, which will help to align our structure along the axis. Next we will go to skewness of LAMMPS. So here is a basic structure which is skewed. So for example we have these box vectors, 4 into 4 into 40 Armstrong structure. So firstly we will be skewing the structure in the YZ plane by a value of 1 in the y direction. Then we will be skewing it by another 2 in the positive y direction for the YZ plane. And if we try to use this structure in LAMMPS, we will find the error. The main reason is, you see that here I have marked this one as y2 and the 3 as y3. So according to LAMMPS, the value of y3 needs to be 0.5 plus or minus into y2. So here the value of y2 is 4, and so y3 needs to be in the range of -2 to +2. So what we can do? What we can do is, since we are skewing the structure by 2 from 1, we can skew the structure in the opposite direction. So we will find -1, and this falls into the allowed range for LAMMPS, and it can be one form of solution. And we can automate this process by using the option unskew, and this can be stored in LAMMPS and can be run in LAMMPS. Next we will go to atoms outside the box. So firstly we create a structure, FCC structure of aluminum using a lattice parameter of 4.046. Next we will shift the atoms. Here you see I have used the option shift 10 10 10, where I will shift the atoms by a value of 10 in all the directions and store it in the .xsf file. So if we try to visualize this in Ovito, we will find that the atoms are here, the simulation box is here, and there is a small mistake, it would be atomi. And if we visualize this in atomi, we will find that the structure contains all the atoms. Moreover, you can also see that the number of atoms here are much more than the number of atoms here. So why is all the changes made here by atomi? So what happens is that atomi uses periodic boundary conditions which bounds all the atoms within the simulation box. Moreover, since the number of atoms is less, or it occupies very little area inside the simulation box, it duplicates the number of atoms by a factor of 2 into all directions. So this is the reason why you are seeing so many atoms within the box. So how do we bypass this? How do we transfer these atoms into the simulation box? We use the option wrap. So what wrap does is, it takes the atoms and wraps it inside the simulation box. Now we will be seeing all this using some example problems. So I create a structure ATOMSK, create FCC 4.046 aluminum m.xsf. So our structure is created. You can also visualize this using Notepad or Oviedo. Now what we will be doing is we will shift this structure ATOMSK aluminum.xsf, shift 10 10 10 aluminum shift.xsf. So you see our whole structure is shifted. So if we run Oviedo, firstly we find out aluminum.xsf. This is our structure. It is within the simulation box. Now after we perform the shift option, we will see that the atoms are far away from the simulation box. Now we will see how wrap works. So we are taking ATOMSK aluminum shift.xsf, wrap aluminum wrap.xsf. So here we have wrapped our system. So if we visualize this, we will see that all the atoms have returned inside the simulation box. So for this skewness and alignment, you can also run the example codes that are inside the tutorials of the website. Thank you.